topic, just this one example to finish up, and then we'll move on to shear and moment. And then at that point, right before we start talking about shear and moment, I'll take a minute to look at the schedule and see what's coming up in the next couple weeks, because we do have the first exam 2 weeks from today. So we'll take a look at that, and then we'll roll into shear and moment. So the focus today will be after this, with shear and moment, we'll focus on applying it to frames. So you've seen a lot of it with regard to beams. Not going to repeat much of that, just go over the basics, and then we'll just apply it directly to frames. So that's the plan for today. So with this cable, all right, so as a quick recap, right, remember we looked at arches and cables last time, and with the cable, the extra equation that we get, it basically comes from assuming the deflected shape. And so with that geometry, right, and we assume that the deflected shape consists of straight line segments between supports and point loads. If we know one of the vertical distances, then we can find all the reaction forces, because with a cable, it's going to be pinned at both ends, so we're always going to have reaction forces. Technically, it'll be probably like that. We'll always have reaction forces, 2 at each end. So we need that extra right, lift, if you will, to get those 4 unknowns, and that is going to come from the geometry. So that is our strategy. And here in this example, we have a cable with 4 segments, all right? So 3 point loads, and the support at E has a vertical difference from the support at A. Our approach is going to be very similar to what we did with arches, all right? So we're going to first write the equilibrium equations for the entire structure, and we will end up with 2 equations and 2 unknowns in terms of either the support at E or the support at A, all right? And then we will take a section at the cable through the joint where we know the vertical distance, right? So we have to make that cut here. We can't get anywhere if we make a cut at B, really, because we don't know this geometry yet, right? Same with D. So we have to start with the point where we know the vertical distance. And from there, we can get all the information we need to solve for the reaction forces. Once we have those reaction forces, we can march through and find all the cable tension, right, for each segment, and we can find the other vertical distances to points B and D. So we'll get going on that. So first, we'll write those equilibrium equations for the entire structure here. Stay. So I'm going to sum moments about E, and we'll end up with 2 equations in terms of AX and AY. That's a little too much there. There we go. All right, so from that, we'll get negative 6AX minus 140 AY is equal to negative 4,500. So that's our first equation. Then, again, cutting through the structure at C, we want to use the left side of that cut because that also gives us AX and AY. So then we'll have the same 2 unknowns in a second equation. And so here we'll sum moments about C, right? And so remember, it's important to keep in mind that when you do make that cut, you technically are exposing the internal tension in member CD, all right? So that is an unknown on your free body diagram, but if you sum moments about C, you don't have to know what it is to get AX and AY. So we end up with negative 16AX minus 70AY is equal to negative 600. All right, so that's our second equation. And then from those two equations, we get AX is 129 kips to the left, and AY is 38 kips acting upward. Now we can go back to the entire structure, apply the remaining equilibrium equations, right, sum of forces in X and Y to get EX and EY. So we would find EY is 27 kips upward, and EX is 129 kips to the right. So notice that the two horizontal reactions are equal in magnitude and opposite in direction, right? And that checks out because we only have vertical loads applied to this cable. And remember, if you only have vertical loads applied to the cable, that means that the horizontal component of all the cable tensions will be the same. So in each of these segments, the horizontal component is going to be 129 kips. Because if you just consider joint E, for example, right, and you sum forces in X and Y, that horizontal component has to counter EX. And it's going to be the same all the way through. And that's only true if you don't have any horizontal component applied to the cable, right? No applied loads that have horizontal components. So just keep that in mind. All right, any questions so far? Okay. So now we can march through the cable and joint by joint find cable tensions and the remaining geometry. This is very similar to method of joints for trusses, to be honest, because you know, in this case, you know the direction of the force is going to be the same as the direction of the length of the cable, right? The direction of the geometry. So that's very similar to trusses. And so we can use those same principles to solve for a cable problem. So at joint A, right, what we want to find is the tension in AB, and we also want to find the vertical distance. I think I labeled it as Y1. Yeah, so it's labeled as Y1 previously. We'll just be consistent. So we'll say if we extrapolate point B to over here, right, this will be the distance Y1. And the horizontal distance from A to B was given as 30 feet. So the tension in AB is simply equal to the square root of the sum of the two components squared, right, H and V. If we look at this joint, right, we know H has to be counter to the horizontal reaction and V has to be counter to the vertical reaction. So we can simply say the tension in AB is equal to square root of 38 squared and 129 squared added together. And that gives us 134 kips. And then to get the geometry, right, there's a couple ways you can go about doing this. I'll demonstrate it slightly differently for each of the joints, just so you can see a couple different options. So for this joint, we'll find that angle, theta AB. So that's equal to the inverse tangent of the vertical and horizontal components of the cable tensions, because those components of the tension force are proportional to the components of the geometry, right? So that's 16.6 degrees. And then what we're really after is this vertical distance y1. So y1 is equal to the tangent of 16.6 degrees, which would then give us, or wait, no, I messed that up, sorry. So the tangent of that angle will be equal to y1 divided by 30 feet. Okay. So y1 comes out to be 8.84 feet. So now we'll go over to joint E, because that's the other easy one to start with since we know the reactions at E. Here we want the tension in TDE and the vertical distance to point B, which we'll call Y2. So point D, if we put it down here, extrapolate that out, that vertical distance is Y2. This horizontal distance was given as 40 feet from D to E. And remember, we have a 6 foot, let's see, so actually what I'm gonna do is I'm gonna measure, to be consistent, I'm gonna measure Y2 from point A. So let's do this. So I'll say that's A. All right, and then there's a 6 foot vertical difference between A and E. So the tension in DE, again, is just the square root of the sum of the reaction forces. So we get 132 kips, very close to the tension in AB. And then for the geometry, I'm just going to use similar triangles. So the vertical distance from E to D is going to be Y2 minus 6, and divide that by the horizontal distance from D to E being 40. We're going to set that equal to the vertical component of the tension, which is 27, over the horizontal component of the tension in DE. So we can then solve for Y2 without even finding the angle. And that's my preferred approach. And this, again, is measured from A. But feel free to take whatever path you like to get there. So then we're just left with joint C and 2 cable tensions to find from there, right? So we still have 2 unknowns. That's the tension in BC and the tension in CD. So let's say that's what we're after. So the geometry is kind of marked out here. We'll say this 16 minus y1. All right, so that is, we go back to the total. All right, this is saying 16 minus y1 is the distance between B and C. All right, so we're going to be looking at that triangle. And then on the other side, we'll measure 16 minus y2 to get that vertical distance from C and D. So we'll be looking at this triangle on the other side. So 16 minus y1 will give us 7.16 feet, and 16 minus y2 will give us 1.63 feet. And using, right, the geometry with the horizontal distances provided here, we can calculate the segment lengths. So BC would be 40.6 feet, and CD would have a length of 30.04 feet. All right, so then from summing forces in X and Y, we'll get two equations with two unknowns, so we can solve for those tensions. So from sum of forces in Y, you would get 30 kips is equal to 7.16, and this is again using similar triangles. So 7.16 over the cable length, 40.6, times TBC, plus 1.63 over the other cable length, 30.04, times TCD. And then from summing forces in X, you would have 0 is equal to 40 over 40.6 times TBC minus 30 over 30.04 times TCD. And so solving those, we would get TCD of 129 kips and TBC of 131 kips. All right, so as a quick gut check, TCD came out to be 129 kips. That's the same magnitude as the horizontal reactions, same magnitude as the horizontal components in each cable segment. But TCD is not perfectly horizontal, right? So in reality, this is rounded slightly. It's probably 129 plus a small fraction, okay? But if we look at the cable, it's the closest segment to being horizontal among all four of them. So it makes sense that the cable tension is the closest to the horizontal component, right? Questions? Okay. Now you know how to analyze a cable. All right, so looking ahead, here we got our schedule. Today we're going to start talking about shear and moment, and then next week that lecture sort of continues into elastic curve. And then on Wednesday we'll start talking about, well, actually, we might start talking about finite element analysis on Monday, because the elastic curve is not, that's not what I keep meaning to do. The elastic curve is not a very lengthy lecture, so this probably will not take up an entire class. So depending on how much time we have left, we might start FEA on Monday. So just be prepared in case we do. However, elastic curve will be the last topic that is on exam 1. So exam 1, 2 weeks from Friday. I'll have more details for you as we get closer, but just basic stuff. You'll be able to bring a note sheet, 1 page, both sides of your own handwritten notes, right? 8.5 by 11, the usual. And it'll cover lectures 1 through 11, all right? Elastic curve. I can note that down here. So lectures 1 through 11 on exam 1. And then I'll have a review sheet for you that I will put together that'll list the topics and things like that, logistics and whatnot. I don't usually dedicate a whole lecture to exam review, but if we have time during the week, I'll try to block out a chunk of time to answer any questions that you may have, or if there are any topics that you'd like to hear a little bit more about, I'm happy to address that if you request it in advance. So that's what the next couple weeks will hold for us. And then after that, we're going to continue with finite element analysis, and then we'll be going into load specification stuff. So yeah, this class is moving quickly. All right, any questions on the logistics? All right, good deal. On to shear and moment diagrams. All right. Oh, there we go. So basically, all right, as you are familiar with this topic, we use shear and moment diagrams to visualize how a structure will respond to a given set of loads. Most commonly, you've seen this with beams so far. The nice thing about these diagrams is that they allow us to readily pick out the location of maximum internal forces, right, maximum moment, maximum shear. And we can also just see how it varies along the length of the beam internally due to a given set of loads. So we just outline the basics using the concept of a simple beam with a uniform load. The relevant reactions are the vertical ones, right? Because there are no horizontal components of applied loads. We only have vertical loads. So we know that there's a horizontal reaction on one of these sides, but that's going to be zero. We're only concerned with the vertical reactions. And from, I think it was, Wednesday's lecture, right, we looked at this condition and I said commit to memory the formula for maximum moment. Does anybody remember what that is?
WL squared over 8.
Yeah, very good. Yeah, so the maximum moment is WL squared over 8, and the reaction forces will be equal in magnitude, right, WL over 2. So this is just a very, very common condition that we see in structural engineering. Many beams have simple supports and uniform loads on them. And so this just becomes really, really beneficial to know off the top of your head so you can quickly calculate reactions and maximum moments. All right, so now if you cut that beam, right, through section AA, for example, you expose the internal moments and shears. Positive directions are shown here, all right? So note that the positive direction changes depending on which side of the cut you're looking at. That's consistent with the positive directions shown here on either end of a segment, right? So what we have are the positive directions for X, B, and M shown here. As you know, positive moment tends to cause the beam to bend so that it forms a smile with tension on the bottom fibers and compression on the top fibers. And I can write that. Over there. And if we plot, right, the internal values for shear and moment along the length of the beam, we know that there are some relationships between those two diagrams, right? So for example, the slope of the moment diagram is equal to the value of the shear at any given location X. And the change in moment between any 2 points on that moment diagram is going to be equal to the area under the shear diagram between those same 2 points. And below that, we have the general expression for m of x, right, related to the integral of shear. And we have to add to that any potential concentrated couples or concentrated moments, right, that might be occurring. So to break that down, right, we'll talk about the sign convention here. So a couple that causes a clockwise moment about a point will result in an upward step or a positive step, I'll say. Upward is appropriate if it's a beam, but not necessarily if it's a column, right? Because then you orient your shear moment diagrams a little differently. So I'll say positive step. And conversely, a moment that causes a counterclockwise rotation about a point will result in a negative step within your moment diagram. So this is a little bit counterintuitive, I always find, for students. And I remember as a student myself being confused about this sign convention. So this is why I noted in the equation, instead of plus minus, I noted minus plus as a reminder that, you know, think about the sign a little bit carefully before you just add that value. So the reason that a clockwise moment generates a positive step in your moment diagram is because if we consider a beam segment, all right, where you have such a thing, a clockwise moment at a point, if we think about the deflected shape that that moment will cause, all right, and we'll consider fixed ends in this case, that deflected shape would look something like this. All right, so the emphasis is really on what's happening at the point. With that clockwise moment, it'll want to push the right side down and the left side up, right? So that's that positive couple effect. Now, if you are marching along this beam left to right, because that's in our positive x direction, then at any point before you reach that moment, right, let's just say this section right here, your moment value is going to be negative. So I'll just note, actually, what I'm going to do is this. I'll just draw little sections, all right? So if we take a section on the left side of the cut, all right, that clockwise moment has the effect of negative bending, all right? Looking at our sign convention here, the right side of a segment would have positive counterclockwise. Since we have clockwise on the right side of any point before we reach that moment, that's a negative m. Once we get to the other side, all right, now we have, we'll just say, here's that side, and then any other point over here. Now we have also a clockwise moment, but it's positive on the left side of a segment. All right, so the applied moment in a clockwise direction will have a different effect on the bending of the beam on its left side and its right side. So that's why we end up with this result. With the shear force and concentrated vertical forces, it's more straightforward and more intuitive, right? So you have a positive force generates an upward step or a positive step. Be more generic again. And a downward or negative force generates a negative step. And once again, I just want to emphasize that we always, for beams, always take our x value as positive left to right. Questions? Okay. All right. So on the next page, we have some, I guess, shortcuts, if you will, for estimating or calculating areas under that you may see under shear moment diagrams. So as you know, right, it's also necessary to be able to locate the centroids of these areas for calculating certain points in your moment diagram or distances. And if you have a constant shear, you know that means you're going to have a linear moment and so on. So this is in order of increasing magnitude. And you can notice the pattern here, right? The area under the curve goes from 1 to 1/2 to 1/3 to 1/4 of b times h as you increase in degree. And similar for the centroid, right? So this could continue in trend. If you had a quartic relationship, then it would be 1/5 bh for the area, right? And 1/6 b for the centroid. And for diagrams to be considered complete, right? Check all the boxes here. Make sure that you include all maximum minimum values, both absolute maximum and minimums, and also any local maximum and minimums, and any corner values. By corner value, what I mean is, if your shear diagram, for example, does something like that, these are your corner values. Make sure your diagrams are labeled with units, and it's always a good idea to verify that those diagrams close to 0. If they don't close to 0, something's wrong, right? One way you can do that is after you've drawn the diagram, you can double check by coming from the other direction. Sometimes that's easy to do. Sometimes it doesn't make sense. So yeah, but there are different ways you can do that. All right, so now let's launch into applying this to frames. So first of all, we've talked about and are familiar with, right, the sign convention for a horizontal element, right? So you have your positive x left to right, and then your positive shear or moment is plotted upwards on the graph. If we have vertical members, we're just going to take this and rotate it 90 degrees counterclockwise. So your x will be positive upward, and your positive shear and moment will be to the left. Right, so then it follows that your sign convention for vertical elements will be also rotated 90 degrees counterclockwise. So that's your positive shear and moment for positive x upward, right? So one thing I don't want to see for vertical plots, I don't want to see positive x downward, and I don't want to see something like this, all right, where positive shear and moment is to the right instead of to the left. Some folks are more comfortable just taking the shear moment diagrams for a vertical member and plotting them, right, rotating them back down to what it would be if they were horizontally aligned, and that's fine if you want to do it that way, but it's nice to be able to plot the shear moment diagrams consistent with the orientation of the member that you're drawing, because then you can really see where the corners will match up and things like that. So I encourage you to do it that way, but if you want to plot them, treat them as horizontal elements for the plots, that's okay. For your free body diagrams, please make sure that they are oriented properly. All right, so we're going to look at this frame. We have pin supports at, or one pin support at, we'll call this A, and a roller support over here at D. So this is a simply supported frame. It is stable because we have rigid joints at B and C. All right, so remember when we talked about rigid joints, what is the characteristic behavior of a rigid joint?
Stays at 90 degrees, so it doesn't rotate.
Exactly, yeah. So that rigid joint will maintain 90 degrees no matter how the frame deflects, right? So the joints themselves can displace, they can move depending on the loads applied, but the members have to move and rotate by the same amount and in the same direction at those points. So applying statics, right, to the overall frame, you can find the reaction forces, and it's usually necessary to find the reaction forces for a frame before you find any of the internal forces. So sometimes with trusses, or I guess more often with trusses, you can get away with not finding the reactions first before you find internal forces. But with frames, that's much less common. An example of being able to do that might be if you had a cantilever extension on this side maybe, and some load on here, you could break that off, all right, because you have a free end here. You could break that off and have 3 unknowns at the rigid joint, and you could solve for the forces at that joint before you get any reaction forces, all right? But for a frame like this, you have to find the reaction forces first. So those are listed here. We'll apply them on the next page, and I don't know what that is stuck on there. So we'll apply them on the next page, and we'll work our way through the frame to find all the internal forces. So first, we'll write those reactions on the free body diagram. And this is what we call an expanded free body diagram because we are breaking the individual columns and beams apart at the rigid joints to expose the internal forces that are transferred through those joints. That was 51 kips at D. And then this is B and C. So I'm going to go ahead and draw on here the internal forces at the joints. All right, so we have BX, BY, and a moment, MB. And then over at joint C, we'll have CX, CY, and a moment, MC. Now what I did here is, at joint B, I just assumed positive directions for all the unknowns. When we go through the math, the sign that we get will tell us whether that's correct or not. And then over here, I applied a little bit of intuition, right? So you know that the vertical reaction is upward. That means the force at CY has to be downward. The only load applied is to the right on this member, and there's no horizontal reaction at the base, so the horizontal force at C has to be to the left. The moment at C was just kind of a arbitrary positive assignment, so we'll find out whether that's correct when we go through the math. And then once we know the actual magnitudes and directions of these forces, we will transfer them to the beam. So they'll be equal in magnitude and opposite in direction on the beam ends. Now you could do that at this point, right, and write them all out as unknowns. And you could, if you wanted to, march through and find, you could find, the forces at joint B, for example, and then transfer them here, and then solve for the forces at C, and then transfer them down here. But the approach that I'm going to take is actually going to analyze the two columns, solve for the forces at B and C, and then just transfer them both to the beam. So So we'll start with AB. And from summing forces in Y, we get BY is equal to 22 kips downward. From summing forces in X, we get BX is equal to 20 kips to the right. And from summing moments about B, we have our unknown moment at B in the positive direction plus 60 kips times moment arm of 10 feet, also in the positive direction. And for this positive direction, right, this is just tied to whatever direction you assume as positive for summing moments. It doesn't have to be positive counterclockwise. That's a habit that we have that's been drilled into us from statics. And it's a good habit to start out with because it gets you into a pattern. But at this point, you know, feel free to break away from that. If you want to assume positive clockwise, go for it. It doesn't really matter as long as you're consistent throughout the entire equation. So then that 80 kip force will cause a negative moment about B with a moment arm of 20 feet. And I'm going to run out of room, so I'm going to shrink this a little bit, move it over. So we get the moment at B is equal to 1,000 kip feet counterclockwise. So the assumption of a positive moment at B was correct for member AB. For BC, or excuse me, for CD, all right, we'll sum forces in Y to confirm that CY is equal to 51 kips downward. Sum forces in X to get CX is equal to 20 kips to the left. And then we'll sum moments about C to get MC plus the only force in this case that causes a moment about C is the applied force. So that's the 20 kip force in a positive direction with a moment arm of 10 feet. So MC comes out to be negative 200 kip feet, which just means that we assumed the wrong direction. So that translates to a clockwise moment, which will be plotted negative on our moment diagram because according to our sign convention, a clockwise moment at the top of a column will be negative. So now going through and plotting shear and moment diagrams, I'm going to add labels or units to these. So our shear diagram for the column, we start off with an 80 kip horizontal force at the base, and then it's going to be constant until we hit that 60 kip load, which will take us down to 20. And then the force at B closes us to 0. The moment will start off at 0 because it's a pin support. Will increase in magnitude to 800. So that's 80 times 10. And then it will increase at a slower rate to 1,000. And then this positive or this counterclockwise moment, right, at B will cause a negative jump in our moment diagram. Even though it's a positive moment at B, it's going to cause a negative step in our moment diagram to 0. So it still checks out though, right? Because at B, we have a positive moment. The value at our moment diagram is positive, right? So it can be very confusing, but it just takes some practice to get the hang of it. So over here, we have nothing on our shear diagram until we get to that applied load, and then it will be constant until we get to C. All right, and then that force at C closes us to 0. Moment diagram, similar. It's going to be 0 until we get to the applied load, and then it's going to increase in magnitude in the negative direction linearly to negative 200. And then this moment, the clockwise moment at C, is going to cause a positive step in the moment diagram. All right, so we close to 0. Now transferring our forces to the beam, all right, again, equal in magnitude and opposite in direction. So By we found to be a downward force on the column. That means it's going to be an upward force on the beam. And that value was 22. Bx is 20. On the beam, it'll be to the right, or excuse me, to the left. And the moment at B, since it was counterclockwise on the column, it's going to be clockwise on the beam. And that was 1,000. Over here, Cy was downward, so it'll be upward on the beam, and that was 51 kips. Cx will be 20 kips to the right on the beam. And the moment at C will be counterclockwise on the beam, 200 kip feet. So drawing the shear and moment diagrams. We have 22 kips on the shear, constant for 10 feet, and then jumps down to negative 51, and then constant until the end, where that vertical force at C brings us back to 0. So this is 22 and negative 51. Moment diagram. We start off with a clockwise moment of 1,000. Is that going to be plotted positive or negative on our moment diagram for the beam?
Positive.
Yeah, exactly. Positive 1,000. I think that's what that 10 was left over from. All right, so that's that point. And then we'll increase linearly for 10 feet to a value of 12,200. And then we'll decrease linearly to positive 200. So then this value, right, we have a positive moment at C for the beam, right, because this is a moment that will tend to cause that beam to deflect downward and smile. So that should translate to a positive moment on our moment diagram. And that concentrated moment will cause a negative step in the moment diagram to close it to 0. All right, questions? Okay. Well, we're out of time. On Monday, we'll just wrap up with a few comments on this example and then roll into elastic curve and then possibly finite element analysis, right? Have a great weekend. Thank you.